Hello, this is lecture 2 from vectors from the topic of basics of linear algebra from the introduction to data science. Okay, so far we understand what is a vector, how we can present vectors, and also we are now familiar with some special vectors, and also in particular unit vectors and how we can express any vector in terms of the unit vectors. So in here we wanted to talk about how we can manipulate vectors. So like any space, in vector space, we should get the vectors, we should be able to add them up, we should scale them. There are two basic operations defined on a vector space, and these two properties are addition and also scalar vector multiplication. This is important when it comes to the terms of multiplication in data science. You should be very careful because multiplication of two vectors, multiplication of two matrices, we have different definition of multiplication. But addition is, however, kind of straightforward. So for addition, if you have two vectors, let's say vector x belongs to, let's say, real numbers. Let's use dark color. It's visually better tractable. Let's say x is a vector belonging to real numbers of dimension n, and y is another vector belonging to the real numbers, and this vector should have the same dimension n, otherwise we cannot do the addition. This is important to note that when you're adding two vectors should have the same dimension. And this is very obvious, but unfortunately when you implement a code and you wanted to add up two vectors, many times we get this error that dimension mismatch. And the reason is we didn't take care of having the same dimension at the first place, or we are lacking what's going on behind the scene. So therefore, pay attention, the dimension of two vectors that are going to be added up should be the same. So if you wanted to sum up these vectors, and then addition is taking place element by elements. So if x is, whose elements are x1, x2, xn, and if y elements are y1, y2, yn, then x plus y is also a vector, whose elements are x1 plus y1, x2 plus y2, and xn plus yn. In other words, the vector space is closed under sum. So that means if you have two vectors, you sum them up, then the resulting vector is also in the same space, same dimension, right? So I see that the dimension of this vector is 1, 2, 2, n. And scalar vector multiplication, that means that we can multiply a vector by a scalar. So let's say A belongs to R1, so that means A is a scalar, single number. Could be an integer numbers, could be also real numbers, any type of numbers, but for the sake of simplicity, I use R in here. You know that R denotes the set of real numbers. And then we can define A times X, A times X. We usually use this, or we can also use A times X. We should be careful about using this notation. Sometimes some texts use dot, A dot X, but this is not, we don't use it in here because this might be a mistaken of a dot product. So don't use this notation for here. So A times X is equal to AX1, AX2, AXN. That means this scalar is multiplied by individual elements in the vector. It's very straightforward, nothing very special. These are also have some definition. That's scaling a vector. That means you're either extending that vector, expanding that vector, or squeeze it, stretch or squeeze. So in other words, if you have a vector like X, right? Let's go, this is X. If you multiply X by A, so if you multiply X by A, if you multiply X by A, so this is X, and if you multiply X by A, then so if A is greater than 1, then we're stretching our vector. So the larger vector, A times X, right? So, and also if A is smaller than 1, then we're squeezing our vector. So these are two basic vector operations. So also we can have an example in here. You know, if I think it should be clear for you how to multiply. Other operation is linear combination of vectors. So far we talked about how we can sum up two vectors, and we can do the vector multiplication. So we can combine these two operations, and that will lead to a linear combination of vectors. So imagine we have these vectors like v1 and v2 and vn. They all belongs to real numbers, and they all have dimension of n. And also let's define a1, a2, and an. These are all scalars, and then we can have a vector v, which is a linear combination of these vectors. That means we first scale each vector, a1, v1, plus a2, v2, plus all other vectors, and lastly the last one, an, vn. So this is called a linear combination of vectors. That's very important, because this is like you have a machine, then you can combine different machines. These machines, let's say you are having machines with one input and one output, if these machines are linear, you can combine them and you can scale them. This is basically how we transform the data, some vectors, and make new vectors. Also, this also has another application in regression models. In regression models, we wanted to express an observed vector in terms of some predictors or covariate. So when we talk about the regression, so in this, for instance, in a regression model, we use this linear combination of vectors. That's very important. So in there, this is an observation, V is an observation, and these are predictors, and A's are coefficients. An example, let's say we wanted to see if we can express the grade of students in terms of his family net income, and also the number of hours he or she studies, right? So then we can find a combination of these two vectors. One vector present the family income, another one present the number of hours he studies. So is there any combination? We can combine them and multiply them by these coefficients. This is a very important topic, and also that linear combination has enormous application in data compression. So when we have a vector, we wanted to present this vector into some basis vectors, and then because we know these basis vectors, we just want to compute a coefficient and send this coefficient over a channel, and then reduce the dimensions, right? Imagine this is the data you wanted to say V, and then you project it to some space, and in this new space you found that all coefficients except one is 0, and then the sender and the receiver, they're all aware of these vectors. So all you need to send is the coefficient. So that's, I can talk about this for an hour, about the linear combination of vectors, but I wanted to say that these are not some abstract math formula. They have real applications. Okay, element-wise vector multiplication. So if you read some papers on deep learning or neural networks or many other topics, I just mentioned deep learning because this is a very popular topic for prediction and pattern recognition these days. You will see that a notation looks like this. Something like this, circle with a dot. So you may wonder, what is that? So as I said, when it comes to matrices, vectors, we define different type of multiplications. One of these multiplications is element-wise vector multiplication. Element-wise vector multiplication means we are multiplying the elements of two vectors element by element. So what does it mean? I'm going to give you an example. So this is the notation we use. And when I say x dot product y, note that this is not very, it's not standard. Some textbooks, some authors, they may use different way, but this is very common to use this notation. So this means that let's say if x is a vector I can have a general definition, but I feel that if I give you a simple example, you can better understand that just dealing with these abstract numbers or a generalized formulas. You can easily, for this example, extend it for a general case. But for sake of simplicity, let's say this vector is 5, 2, and 1, and we know that x belongs to set of integer numbers, and dimension is 3. And then we have another vector y, which is, let's say, 10, 0, and 7. Y also belongs to set of real numbers, dimension 3. Then x dot y is element wise. So that means we do the multiplication. 5 times 10. First element, the second one 2 times 0. So 1 times 7, right? This is equal to 50, 0, and 7, right? So this is element-wise operation. We multiply the element one. The reason we call this one, because we also have inner product of vectors, and also we have the matrix multiplication, which is quite different from the element-wise operations. But in many applications and algorithms, we need to multiply element by elements, right? So for instance, let's say you have a vector of like this, like 5, 6, 10, and you wanted to weight elements of these vectors and sum them up, right? Let's say I wanted to, let's say this is x, this is w, w are the weights, so this weight of the first element is 0, the weight of the second element is 2, and second element weights is 3. I'm sorry. So then, if you want to do weighting, we use the element-wise multiplication. Sorry. This is 0, 12, and 30. Then we can sum them up, right? So that's element-wise vector multiplication. And perhaps one of the most popular vector operation is inner product, that has enormous application. Also, we call sometimes that one a dot product. You have done the inner product in high school, but basically there they call it something else, something a projection of vector in another vector. But in here we are giving a formal definition for inner product. So, so inner product of two vectors is, there are different notations we can use. Either sometimes we use a dot, so we use note that. Different notations are used. So the first one is x dot y. The second notation is x and y. They put them in egg. The third notation is x transpose dot y. Right? The fourth notation I've seen they use dot x and y. Right? So in any of these cases, the dot product, so we use either the first notation, or we use all of them throughout this course, but just have in mind that these are all have the same output. So in order to have a definition for inner product is the inner product is defined as the element-wise multiplication of elements and then sum them up. So if X belongs to Rn, know that I use the real numbers, but it could be any other spaces, right? And then if Y belongs to Rn as well, and then we define the X dot Y, and then if X is defined as X1, X2, all the way to Xn, and then if Y is defined as Y1, Y2, Yn, then X times Y is equal to X1, Y1 plus X2, Y2 plus Xn, Yn, right? Or in a very compact form, which I recommend you to understand it through this notation, X dot Y is equal to the sum over I equal to 1 times to N Xi Yi. That's another definition of inner product. So I would like to spend some more time on inner product because we are going to use inner product extensively throughout this course, and also there are different notation, as I said. I wanted to make sure that you understand all this notation. So one of the source of confusion is when we have the X dot Y or X dot Y. So when we have this notation for inner product, this basically is a if we define a vector as a matrix, then we can define it as this represents an inner product. So what does it mean? That means basically this is a simple matrix multiplication. So that is a matrix multiplication. Therefore, we will say what is the matrix multiplication. But if you wanted to multiply, so this one is clear, but for this one I wanted to just remove the ambiguity you see. So if you wanted to multiply a matrix by dimension of m by n to another matrix Y, then the number of columns of the first matrix should be equal to the number of rows on the first matrix. This matrix multiplication is therefore, if we call it Z, is equal to m times k. So now imagine X is a vector. So usually we use this notation for a vector as n by 1. This is how we use the notation of vectors. This is a vector of dimension n by 1. And then also Y is n by 1. Now, if we consider them, both of them as two matrices, and we wanted to multiply these two matrices, then the inner product is, or we can say the X dot Y is equal to X transpose times Y. So that makes sense because we know that if X dimension is n times Y, then X transpose is Y times n, right? Because in transpose we basically swap the rows with columns. I give you a formal definition for transpose, but for now it's how it looks like. And then I can do the multiplication. That means X dimension is now 1 times n times y, which is n times 1. Now this is equal to z, which is 1 by 1, right? Which is a scalar. It's a scalar. This is also important to note. The dot product of two vectors is a scalar, is a number, is not another vector, right? So the dot product output is the dot product output is a scalar, not a vector, right? That's important to note, that the dot product of two vectors is a scalar. So dot product has lots of interpretations. So I'm not going to talk about all of them, but as we proceed, I will shed more light about the importance of dot product. But one of the, there are a couple of definitions or interpretations that I would like to give you a brief description. The first one is the projection. So when we do the dot product, basically we project the vectors to another one. So imagine that we have this Cartesian plane, and so I can remove this one. This gets confusion. Imagine we have this vector. Let's call this one v, and this vector is, this is v1, this vector is v2. So if you project this vector onto this vector, that means if you project, then this is the new projected, this new projection, right? So basically this green is v2 times v1, and this is equal to v1 v2. We know that this is the dot product has the commutative property, right? So this is one definition of the interpretation of the dot product. We project a vector 1 to vector d. So that's one definition. There's also another definition that the dot product basically presents that how two vectors are close to each other. As I said, we need to have more some other definition and concepts in order to explain more about dot product, but I will leave it when I introduce the norm of a vector and then the angle between two vectors and how they are related to the dot product. But for now, for most of the data science problems, have in mind when you wanted to see how two vectors are close to each other, you can use dot product, but with some caveat which will be mentioned later. So that's another operation, and also dot product of two vectors is a scalar, and also dot product is different from element-wise product of two vectors. Okay. There's also another way of defining the dot product. So we can say this is more looking at the dot product as in more pure math. So as we know that if you have a vector like x belongs to Rn, and then we have y belongs to Rn, so these are our space. So then dot product is a function. It's a function like f, which mapped the Rn to R, right? So we have the vector in the input to the dot product, the output is a scalar. So in other words, if this box represent the dot product, then we have two inputs, so two vectors, x belongs to Rn, and also y belongs to Rn, and then the output is R, which is scalar. So the output is, let's say A is a scalar, right? This is the, sometimes they put it in the form of a function. Dot product is a function. So also I reiterate again that we have different notations using different literatures in order to present the dot product of vectors. X dot y, x transpose dot y, and also put in the, so x, y, these are all the definition of dot product, dot x and y, okay? As I said, there are tons of application for dot product. I give you a couple of them that you're going to use at least in very advanced data science, in particular when you're dealing with working with documents and words in natural language processing. Most of the application of today's data are dealing with text. So you're given a file of like 1 gigabyte of text. You should clean it, and then you should extract some knowledge from this data. As I said, one of the application of inner product is pick one elements of a vector, right? So how do you think we can, using inner product, pick the ith element of a vector? So there are two reasons why you bothering to talk about this, because as I said, most of the operations in today's machine learning algorithms, prediction algorithms, are optimized on GPUs, CPUs to deal with vectors. So you're supposed to present everything in vector form. And second one, having a vector demonstration make easier to understand the algorithms. You don't need to write tons of words, but you can have the a vector illustration of the algorithm rather than the scalar wise, which is very hairy and complicated. So imagining that I have a vector, so let's talk about each of them briefly. We get a new page in here. So I wanted to talk about how to pick the ith element of a vector. So let's say x is a vector, and then whose elements are 3, 15, 20, 9, and 1, right? So x belongs to integer numbers, and number of elements are 5. Is that 5, right? So now I wanted to extract xi, x5, x3. With this in mind that this is the first element, this is the first, this is the second, this is third, this is fourth, and this is fifth. Again, as I said, the index starts from 1, but in programming language in Python, it starts from 0. Okay, therefore the third element in here is 20. Yeah, so yeah, it's very simple to pass x as a bracket 3 and get the third element. But as I said, sometimes we want it to be more flexible and then do the vectorized. How to do this? How we can, using dot product to get the third elements. How can we multiply this vector by another vector such that we get the third element? Any thought on that? Okay, so I think you're right. We need to use the unit vectors in here and dot product. So if I define a unit vector of u, whose elements are 0, 0, and 1, and 0, and 0, so u belongs to a real number of 5. And then if I do the dot product, so if I do the dot product of x and u, this is dot product is what? Is 0 times 3 times 0, element by element, right? So we're multiplying elements by elements. This one, this guy, this one goes this one goes multiply to this multiply here, this multiply here, right? 3 1 0, 15 times 0, and then 20 times 1, then 9 times 0, and 1 times 0. What is the output? The dot product of the x and u give me 20. And I know that x3 is 20. So this is how we do it using dot product, to picking up one element of a matrix. Another very, very frequently used application of inner product is sum of elements of a vector. So I wanted to see how we can do the sum of element of a vector. So let's say you're given a vector x, whose elements are 1, 5, 0, 3, 7. And I wanted you to write a program to sum up the elements of this vector. So let's say this is a coding question. Okay, the simplest coding question ever. Perhaps if you don't know how to do it using in inner product or dot product, you're running a loop, and in this loop you're summing up the elements. But as I said, in data science, and in particular when you're developing algorithms, forget about loops. You should do a vectorized operation. So how we can use a vector product to get the sum of these elements? Again, go back and look at the special vectors we talked. One of them was one vectors, right? So do you remember this vector, the ball, is a one vector. All elements are 1. So let's say I have one vector whose elements are all 1. 1, 1, 1, and 1. Right? And 1 is a vector belonging to a real number of dimension 5. Now, if I do the dot product, so x dot y, because I wanted to be more clear, I use this close open angle to use the dot product. X dot y, dot product of these two vectors, is now multiplying the element by element. So basically I do multiplying elements one by one, this one by this third element, fourth element by fourth, fifth by fifth, and then sum them up. So therefore the dot product of these vectors are 1 times 1 plus 5 times, plus 5 times 1 plus 0 times 1 plus 3 times 1 plus 7 times 1, which is basically 1 plus 5 plus 0 plus 3 plus 7, which is equal to 16, right? 16. So that's the sum of the elements of these vectors. So using the dot product, you can do that. So this is, if you wanted to sum the elements of a vector, you use a dot product of the one vectors and that vector. The other way, averaging a vector. So that should be now clear, right? So if you want to find the average or mean of a vector, right? Using dot product. How you use the mean? The mean of a vector. So that's also very simple. So we already did it using the, so basically what was the definition of mean of a vector? So the mean of a vector, which is just a mean of x, which is denoted by x bar, is equal to sum of all elements in this vector, and then dividing this by n. But we don't want to do this using loop. We wanted to use the dot product. So basically then x is equal to, we already showed the dot product of x and one vector, which is sum of all elements, and then divide this one by n. That's equal to mean. So what is this? This is the dot product, right, of x and one vector. Okay, so that's the dot product of this. The other applications are co-occurrence. So if you have the other one is a square sum of elements of a vector. That's also important because when we talk about the probabilities and also when we talk about standard deviation, we are using this formula a lot. And also when we talk about the error of a prediction, so when you wanted to compute the error of a prediction, we use this dot product. So we wanted to see how we can compute the square sum of the elements of a vectors. So you can also consider these as some sort of practice about vector operations. So then here I wanted to compute the sum of squared element of a vector. What does it mean, the sum of the square element of a matrix? That means if x is x1, x2, xn, then this sum, let's say put it m, or so it's n, or S. Let's put a letter that's very confusing with others. S is sum of these elements. That means x1 squared plus x2 squared plus the other elements also squared and the last one squared. Sum of all these elements. So again, if you wanted to implement this one without any vector operations, you just basically square each element and sum them up in a loop. But we don't want to do this. So we already know how to sum the elements of a vector, so using one vector, right? And then we need to see how we can square the elements of vectors. So in order to do the square of the elements of vector, this is very simple. If we do the dot product, so if I define dot product of a vector with itself, this is exactly equal to x1 squared plus x2 squared plus xn squared. So the dot product of a vector with itself give the sum of the square of the elements of that vector. Okay, so that later on will be used in order to compute mean square error and also in order to compute the standard deviation. Other examples I had in here, co-occurrence, which means that if you have two vectors, you wanted to see if two elements of two vectors at one place they are occurred or not, we can do the dot product. Another one is weight a vector. How to weight a vector. This is very important. I would like to also spend some time to talk about how to weight a vector. So here we want to talk weight a vector. So let's see if we have another topic in here. Vector. How to weight a vector. So what's weighting means? This is very important, as I said, when you have different data and then you want to aggregate this data with different weights, then we do the weighting. Let's say this has enormous applications when different types of data, they have different priorities. And then also sometimes we wanted to use the weighted average. That means if you have three numbers, you want to weight them differently and then sum them up, divide by the number of data. And also, this is also very important when you're computing the covariance metrics in probability. So what is the weighting of vectors? So imagine x is a vector whose dimension are x1, x2, xn. So x basically belongs to Rn. And this is a weighting matrix W whose elements are W1, W2, Wn. And W also has the same dimension, belongs to Rn. The weighting means if you want to weight these elements, that means it's sum of the weights. So that means we are multiplying x1 by w1, x and x2 by w2, and lastly x1 by w1. This is the weighting. This is the matrix of, let's call this matrix H, right? So how to do this? This is simple. We already know H is equal to X dot product of X and W. So this is how we do the weighting, right? This is the weighting. And also we use that one for correlation analysis because correlation needs to know the knowledge of the norm of a vector, and then I will talk about the correlation analysis in details when we talk about the norm and the absolute value of a vector. So these are, in summary, I showed you that the inner product has a lot of applications, and I show a couple of examples in here, but the dot product applications are much more than these few examples. As I said, if you wanted to see how I compute your grade, so we know that, if I'm not mistaken, there are different, I wanted to show one application of vector operations for, at least my case, how I compute your grades, or it's very standard norm for other professors as well. So let's see, in this course, we have 30% for your final. We have, I believe, 30% for homeworks. We have 20% for, say, midterm, and also we have 30%, sorry, 25% for midterm, and also 25, how many left? 25%, we have 60, we have 85, and then we have, 15 for quizzes, 50% for quizzes. So if one student's grade, the grade of a student is like the final one, and then H, M, and Q, then I create a weighting vector, weights vector like 0.3 homework, 0.3, and then 0.25, and then 0.15, and then I multiply, I do the dot product of the grade and weight. Right? So this dot product basically gives me the weighted sum of this, your grade, which is F1 times 0.3 plus H times 0.3 plus midterm times 0.25 plus quizzes times 0.15. And then we can also simply average that, and then your final grade is the dot product of your grades and weights divided by, actually we don't need to divide by 1 because we already normalized that. So this is the way we compute one example of the dot product. There are also other examples, which I am going to explain later. So I'm going to stop here, and then we will continue our discussion on vectors on the next lectures.